Okay, well, hello everyone. Sorry we are meeting like this. Um, I am a real stickler for coming to class and being there on time, but this appointment just couldn't get out of. So we're going to do it this way. I will go over some notes for you for day 6, and hopefully it's not a really tough section. Hopefully that will work well, and we will be in good shape. So let's get started. Day 6 has got in limit rules. So here we're going to get started. We've got A, B, and C are constants, like real numbers. And we're going to let the limit of f as x approaches a and the limit of g as x approaches a exist. There are 5 theorems. I am not going to prove the theorems. I will show you a demonstration of each, and hopefully that will make it much easier. Now, I know probably by now, most of you are ignoring everything I'm saying, and you're madly copying all of these down. I think you'd be far better off if you just be a bit patient. I'm going to give you the conclusion for each one of these, and I think that will be more valid. For instance, on the first one, suppose we wanted to approach A for f plus g. The theorem says that the limit as x approaches a of a sum is the individual sums added together. Okay, so the limit of a sum is the sum of the limit. Okay, and we'll go through each one of these with a demonstration like I mentioned. Number 2, the limit of a constant. That's a real number. Constant times a function like 5x squared or negative 2x cubed. If you have a constant in front of a function, the theorem says the limit of that constant times a function is the constant times the limit of the function. And that's the way I'll write it. The limit of a constant times a function is the constant times the limit of the function. Okay? Number 3, notice this is a product. Well, now you've got it all figured out. You can probably finish it on your own. The limit of a product is the product of the limits. That's almost hard to believe it's that easy. Ditto on quotient. The limit of a quotient is the quotient of the individual limits. So the limit of a quotient is the quotient of the limits. Okay, and the last one is the limit of a power. See, it's raised to the end, is the power of the individual limit. So the limit of a power is the power of the limit. Okay, now I promised you demonstrations of each one of these. Let's look at this one. I'm not exactly sure if these are in the exact same order. Here is the limit of a sum should be the sum of the limits. Now I picked 2 functions. Here's the function f of x equals x plus 1. Hits at 1, slope is up 1 and over 1, right? Straight line in red. This one over here, g of x is negative 2x. It is this line, hits at 0, slope is down 2 and over 1. Now, in each of these functions, I want to approach 1. Back in this first one, when we approached 1, you can see that the function approaches 2. This one, as we approach 1, you can see that the function approaches negative 2. What is the actual limit of the sum? Well, when you add these 2 functions together, negative 2x plus x plus 1, there's the sum. Negative 2x plus x plus 1 is negative x plus 1. Here is that sum. That's the sum. And as you approach 1, what does the function approach? But 0, which is 2 plus negative 2. Pretty cool demonstration that that one does indeed work. Okay, next one. Next one, here's the limit of a constant times a function should be the constant times the limit of the function. I'm going to start with the absolute value function, absolute value of x. As I approach negative 1, you can see the function approaches positive 1. Now, if I take this function times 2, I get 2 times the absolute value of x. What's the graph of 2 times the absolute value of x? Here it is. It's still the classic V shape for an absolute value, but it's steeper. Okay? So what is the limit of 2 times this function as x approaches negative 1? As we approach negative 1, you can see that the function approaches 2, which is precisely 2 times the 1, 2 times the limit of the function. So 2 times 1 is 2, and it works. Okay? This one, while we're here, let's just do this one. You say, well, was that one of the 5? Oh, yeah, right here. The limit of a power should be the power of the limit. So the power I'm using here is a cube root. Cube root would be a power of 1/3. Yes? So I claim by that theorem that the limit of a power should be the power of the limit. So it should be the limit as x approaches 8 of cube root of x. Here is cube root of x right here. As x approaches 8, we can see the function approaches 2. I claim the theorem says the limit as x approaches 8 of x to the 1/3 should be the 2, should be the limit of the function as x approaches 8 to the 1/3, or the cube root. So the limit of a root is the root of the limit, or the limit of a power is the power of the limit. So what is the limit of x? Just plain x. X is a diagonal line. I'm kind of off my picture here. Way over here is 8. As I approach 8, this function, because it's x, it's the same as x, is going to approach 8, and the cube root of 8 is 2. So the limit of a root is the root of the limit 8, and you still get 2. These things are easy, and they're also kind of cool the way they work. Okay? Now, let's do, and just making sure I don't get mixed up here, let's do the limit of a product of a function. So I'm going to use x squared for my first function. I'm going to approach 1. And as we approach 1, we know that the curve approaches 1. Over here in this one, g is going to be x minus 1, hits at negative 1. Slope is up 1 and over 1. As I approach 1, this one approaches 0. Okay? So what is the product of these two functions? X squared times this, x squared times x minus 1 is x cubed minus x squared. I very carefully graphed that. It's a cubic. Looks like this. Now as I approach 1, you can see that the function approaches 0, and the limit of this product is 0. But isn't that what the product of the individual limits is? 1 times 0. So the limit of a product of two functions is the product of the limits. That one is demonstrated. Okay, and this one we talked about. It was the constant times a function and so on. How about the limit of a quotient of two functions? I think that pretty much wraps this up. Okay, limit of the quotient of two functions. I used f of x is equal to 4, horizontal line. Over here, I used x plus 1, slope of 1 over 1, and it hits at 1. I want to approach 2. As I approach 2 on the x-axis, look what the y values approach, which is kind of silly. They're 4 everywhere. In a sense, they do approach 4, but they are in fact 4. Over here, as I approach 2, this function approaches 3, okay? So this is the limit of the quotient of these two functions. I'm going to divide 4 divided by x plus 1, which is right here, 4 divided by x plus 1. This, as you may recall from our last time together, is not going to have a limit as you get closer and closer to, if you get closer and closer to -1, because there's an asymptotic line here, okay? But I'm not asking you for that. I'm asking for the limit as x goes to 2 on a quotient should be the quotient of the two limits. And I very carefully graphed this function. 4 over x plus 1 is here. And as you come in on 2, this approaches that value of 4/3, which is the quotient of the two limits, which is pretty neat that it works out like that. All right, so there's demonstrations of everything that I wanted to talk to you about. Now, let's talk a little bit about the problems, okay? In other words, now that we have all the various rules for limits, can you evaluate a limit? And let's do it by justifying each step. So I want to start with the limit as x goes to 2 of x squared minus 4. Is this not a sum? I know it looks like a difference, but I'll write it as a sum. Is this not the limit as x goes to 2 of x squared plus the limit as x goes to 2 of -4? Yes? Okay. So that the justification would be the limit of a sum is the sum of the limits, right? How about the next one? This is the limit of a power. And don't we know the limit of a power is the particular power of the limit? And let's go over and do this one. Isn't this, well, we can easily say this is a horizontal line going through -4. And we know the limit as x goes to 2 is going to be -4. So that's easy. Okay? This one, the function x is a perfect diagonal. As you get closer to 2, doesn't it get closer up here to also to 2? Square that is 4 plus -4. The answer should be 0. And let's go back and look what we were talking about to start with. X squared minus 4 is a parabola. Hits here and here at 2, 0. Sorry about that. And over here, -2, 0. As I approach 2, right? Isn't that what I'm doing? Approaching 2, doesn't the curve approach 0? See? Okay? All right. Let's talk about a function. Function is said to be a continuous function if it can be drawn without lifting your pencil. This is not the strict mathematical definition, but it is a good definition. If you have to lift your pencil, look at this. That's a function. Each x only goes to one y value, but I cannot draw it without lifting my pencil. So this is not continuous. Functions that have breaks, asymptotic lines, and whatnot are not continuous. The theorem going along with this, a function is said to be continuous if and only if. If and only if means it goes both ways. If it is continuous, like this parabola, right? Then we know that I can simply stick the x value in and find the y value to get the limit, because there's nothing illegal about that parabola. There's no division of 0. There's no square roots of negatives. Okay? So if a function is continuous, you can simply punch in, like right here. I can punch 2 in for that because I know it's continuous. 4 minus 4 is 0. So if a function we know is continuous, you can simply stick the value, what you're approaching, into the function. Okay? And we'll talk a little bit more about that later. This also goes backwards. If we know for every c value that the limit as you approach it is f of c, you know then there are no breaks. There's no breaks. There's no asymptotic lines. So you can be justified in saying that it has to be continuous. Okay, so it goes both ways, forward and backwards. Now, let's get the implication of that in some of the problems. Let's look at this one. We want to approach 3. Is it continuous at 3? Well, yes, because the only place we're going to have a problem is at -4. You get division by 0, yes? So we know at -4 we're in trouble, but at 3 we're okay. I can put the 3 in for x, and I get 9 minus 6 plus 5 all over 7, or 8/7 for that limit, because I know it's continuous at 3. You can simply stick it in. What about this one? Is it continuous at 3? No, we got a problem here. We got a problem. Now, I think we talked about one of these when we were together last. Let's come back to this one. Let's jump over to this one. It's very similar. We still have a problem at 3, don't we? You can't stick 3 in there, okay? So what we're going to have to do, let's see what happens on either side of 3. If you have 1 over x minus 3, and if you stick in numbers that are approaching 3, like 3.1, 3.01, 3.001, if you stick those in, okay, you're going to be left with tinier and tinier fractions. So this becomes 1 over a tiny fraction. And these fractions that are left over when you subtract 3 are all positive. So it's a positive tiny fraction. What is 1 divided by a tiny fraction? Like 1 divided by 1,000. Don't you have to flip the second one and multiply? And doesn't that give you a huge number? So it gives you, pardon me, it's not the empty set. It gives you infinity. So we know as we come in this way, it is going to explode and go up. What about when we come in from the left? Like 2.9, 2.99, and so on. You're going to subtract 3, and don't you still get tiny fractions? But this time, they are negative tiny fractions. And 1 divided by negative tiny fractions, similarly, you flip it and multiply, you get huge numbers with negative signs, which mean that this is going, when you get closer to 3, it's going down this way and it's going up this way. As you approach 3, it's going in 2 different directions. There is no limit. Okay? Now let's go back to this one. X squared minus 9. All good algebra students can cancel out an x minus 3. And this function, x squared minus 9 over x minus 3, is exactly the same as x plus 3. But remember, 3 will give us problems. So x plus 3, what does x plus 3 look like? Isn't it a linear function hitting at 3 with a slope of 1, right? But at 3, we still have a problem. Everything else is fine. At 3, which would go to 6 in that, it is not allowed, and we have a hole. Everything else is fine, okay? It's only 3 that causes a problem, so 6 is out, because you can't use 3. There's a hole. But here's the beautiful thing. As you approach 3, you are still approaching 6. That's the definition of a limit. It's what y approaches. We are not getting there, we're just approaching. And it is still approaching 6. So even though there's a hole, and it's discontinuous here, even though there's a hole and it's not continuous, we can approach a hole. So it is 6. All right? Now we've got some more interesting problems down here. So let's talk about these. I'm going to try to find, how about a piece of paper so I can work on this a little bit better. All right, first one. As h goes to 0, I've got a problem. Got a problem. It's either going to be a hole or it's going to be an asymptotic line. But I can do some work on the top. Limit as h goes to 0, square this out, multiply and double, square the last term, and look what happens. The 9's go away. You can now divide h into each part. Limit as h goes to 0, you get 6 plus h. And that is gone. That h is gone. So we know we can simply put 0 in because this canceled. You know it's a hole. The only thing that's going to cause problem is 0. So we know we're going to have a hole at 0 when you try to put 0 in. It's kind of interesting. It's the same number. It's going to give us 6. Okay? I can put 0 in, right, and get 6 because I can approach a hole. The answer here is 6. Okay? How about a root? Now these are different. Once again, we've got a problem. I cannot put 0 in, correct? But I can do something here. I can do something. Does everybody remember x squared minus 9 factors into x minus 3 and x plus 3? And if you go to multiply these out, don't the outers and the inners go away? 3x and negative 3x, right? These two things are called conjugates of each other because they're both identical, but one is positive, one is negative. So I'm going to go down here and I'm going to multiply by the conjugate. This should always work in a root problem. So I'm going to multiply by negative 5 minus the root and negative 5 minus the root. You got to do the same thing on top and bottom or you'll change the value of the fraction. Okay? And now look what happens. On the top, because these are conjugates of each other, the outers and the inners will go away. So I'm going to take negative 5 times negative 5 is 25. The outers and inners go away, and the root times the root is negative, and the root goes away. On the bottom, just let it like it is. Okay? Because now take that negative in, the 25s go away, and you're left with a negative x, right? And that will kill that x. And on the bottom, the x's are gone. But what's the beauty here? Because the x killed into the x, we know we have a hole, and we know you can approach a hole, like up here, remember? We can approach a hole, so I'm going to put 0 in, and you get the square root of 25 is 5. I get negative 1 over negative 10, or 1/10. Okay? Right? Pretty cool. Last root problem. Okay? It's the limit as x goes to 0. And once again, we have a problem because on the top, we have the root of x squared plus 4 minus 2. And on the bottom, we just have x squared. Putting 0 in causes problems. Okay, so let's try that whole conjugate trick. X squared plus 4 plus 2. X squared plus 4 plus 2. Okay? When you multiply this, they're conjugates of each other. And that means the outers and inners will go away. Root times the root goes away. Negative 2 times 2 is minus 4. They go away. And on the bottom, just write it down. The x squareds go away. And because they go away, once again, we know we have a hole. And you can approach a hole. So now as x goes to 0, stick 0 in. You have a 1 on the top. And you have root 4 is 2 plus 2, or 4 on the bottom. And the limit is 1/4. Root problems, use the conjugate. If you have work to do on the top, do the work and hopefully something will cancel out. All right, let's talk about right and left hand limit argument. And I don't have it written here, but we want the limit of the function as x goes to 4. Let's do a quick sketch. When I'm bigger than 4 up here, I know that everything goes to the square root of x. So 4, I'm not allowed to use 4. Not allowed to use it, but I'll put it in anyway. Root of 4 is 2, but I'm not allowed to use it. Whole. Then the square root function, you may remember it's a sideways parabola. So strictly bigger than 4, it does that. This is the positive square root, so it's only that branch. Okay? When x is less than 4, down here, it goes to 2. I'm not allowed to use 4 again, but it would go to 2, so that's still open. Everything below 4 goes to 2. Okay? So right and left hand limit argument. What's the limit as x approaches 4 from the right? What's the limit as x approaches 4 from the left? Okay? From the right, it is 2. From the left, it is 2. That implies the limit as x approaches 4 from both sides is 2. There's your right hand limit argument. I want to see all 3 parts on a limit argument. Okay? How about a limit argument here? Here we know we're going to approach 0. This one is going to be easy. You know what the absolute value looks like. It's a V shape. So the limit as x approaches 0 from the left, limit as x approaches 0 from the right. From the left, as we come in on 0, do you see the function is also coming in on 0? From the right, as I come in towards 0, the function is heading towards 0. Therefore, the limit as x approaches 0 from both sides is 0. Okay? Easy one. The last one's a little trickier. I can do it right here. Let's sketch it. Now, as you come in from the right, we're approaching 0. So let's write it all down. Okay, as I come in towards 0 from the right, I'm going to have like 5 over the absolute value of 5, 3 over the absolute value of 3, 2 over the absolute value of 2. Those are all the same, 5 over 5, 3 over 3, 2 over 2. So that is all 1. But I can't have 0 because 0 is undefined. It's going to create a hole. Okay? As you come in on 0 from the left, like when you have negative 5 over the absolute value of 5, that's negative 1. Negative 3 over the absolute value of negative 3 is 3. That's negative 1. These are all going to be negative ones, but I'm not allowed to use 0. That's a hole. Okay, we have no tiny fractions to worry about exploding and going to asymptotic line here. Okay, so this also goes now. Sorry, brain dead here. When you have 5 over 5, 3 over 3, and 2 over 2, that's 1, dang it. And down here, we found these to be negative 1. Therefore, the limit as x approaches 0 from both sides is undefined. Okay? This should be a pretty good picture of your homework problems. If you have any trouble whatsoever, I always answer emails. So email me with any problem you have difficulty. Okay? And hope to see you Monday.